Assalamu alaikum students. In today's lecture we will discuss about the phase diagrams. Our learning objectives are phase diagrams definition and basic concepts. Why phase diagrams? Phase diagrams for water when heat is added to the water, when temperature versus heat added and calories will be compared. Phase diagrams for water, a graph of pressure versus temperature will be studied. Schematically sketch simple isomorphous system and eutectic phase diagram. Simple isomorphous system and eutectic phase diagrams. On these diagrams, label various phase diagrams. Discuss about the label Liquidus, Solidus and solvus lines. So how to locate the Liquidus? What is phase? A phase may be defined as a homogeneous portion of a system that has uniform physical and chemical characteristics. Two distinct phases in a system have distinct physical or chemical characteristics. For example, water and ice, they are separated from each other by definite phase boundaries. A phase may contain one or more components. Every pure material is considered to be a phase, so also every solid, liquid and gaseous solution. Graphical representation of the conditions of temperature and pressure at which solid, liquids and gases exist is also called phase. A phase may exist either as a single phase or states of matter or two or more phases in equilibrium when one another. A phase may contain one or more components. A single phase system is called homogeneous systems, where two or more phases or mixtures are called heterogeneous systems. For a pure substance, the pressure temperature phase diagram simply tells which forms, either solid, liquid or gas of the material exists. Which forms, either solid, liquid or gas of the material exist under different PT conditions, pressure temperature conditions. Attached are two types of phase diagrams. One is for the water, the other is for the magnesium. Two variables, one is pressure, the other is temperature. They are plotted against each other for various pressure and temperatures. The substance is water. The water is, if we look at the phase diagram, we can see three types of phases of water: ice, liquid and vapor at different pressures and temperature. For example, at point A, the ice, we can see the phase region. In the phase region, the phase region is ice. When we lower the pressure from A to B at constant temperature, we can see the phase is still solid phase, which is ice. But if we look at the liquid region, in the liquid region, if we decrease the temperature and if we move towards the left hand side towards A, soon this line is crossed, the liquid is converted into solid, the temperature is lowered. Similarly, at solid S point, at a point S, the liquid is in the liquid phase region. In the liquid, if we lower the pressure A point is reached when the boundary of the liquid and vapor is crossed until we reach point E, or as soon we cross the boundary of the liquid and vapor, the liquid is converted into vapor when we lower the pressure. If we look at the point X, the point X is a common point which separates the three boundaries, the liquid, vapor and ice. This triple point, this is called the triple point. The X is called the triple point. Why we call it triple point? At this triple point, the triple point temperature is 273.0098 Kelvin and triple point pressure is 4.6 torr. Why we call it triple point? The triple point because if we change any of the variable slightly, we can easily convert the region from the triple point separates the three regions from each other. Similarly, if we study the pressure versus temperature for the magnesium, this figure shows the pressure and magnesium, two variables for the magnesium, and it is showing the melting, boiling and boiling temperature at 1 atmospheric pressure. Over here the three boundaries, liquid, vapor and solid, are separated with each other through a triple point X at different pressure and temperature regions. If we look at the line XB, this is the boundary line which separates the liquid region from solid region. Similarly, this region, this boundary separates the liquid region from vapor region, and similarly this line separates the solid region from the vapor region. All of these boundary regions are separated by a triple point X at different pressure and temperature. What is the composition of A? What is the composition of A, or what are the types of phases of A if we lower the pressure? Point A. At point A, we can see the liquid, the phase condition is liquid. If we lower the pressure and we cross the boundary, we can get the vapor at a temperature of about between 500 to 1000 degrees centigrade. The temperature is about 800 degrees centigrade. At 800 degrees centigrade, if we increase the pressure is not shown over here. The region, this is the generalized, because this is the generalized pressure temperature diagram for the magnesium. Some basic concepts. Phase diagram provide us with the knowledge of phase composition, and phase stability is a function of temperature, pressure and composition. We will study all these three variables. One of the variable will be constant, the other two variables will be studied with each other, and a graph will be plotted. We will call it a phase diagram. The phase diagram, they permit us to study and control important processes such as phase separation, solidification, sintering, purification, growth and doping of single crystals for technological and other applications. Although phase diagram provide information about systems at equilibrium, they can also assist in predicting phase relation compositional changes and structures in systems which are not at equilibrium. There are two general types of alloys having phase diagrams. substitutional allies and interstitial allies. What are substitutional allies? Substitutional allies have elements which are incorporated into regular lattice positions within the unit cell. We will study about the substitutional allies in iron-iron carbide diagram. The example is tin and zinc allying additions to copper to form bronze and brass. When copper is added to tin and zinc at different temperature, we can get the bronze and brass respectively. Interstitial allies have elements which are incorporated uh, into the interstitial sites of the unit cell. The example is carbon and iron to form steel. We will also study the different types of steel: hypoeutectile steel, hypereutectile steel, with different compositions of carbon. Liquidus and Solidus temperatures. The liquidus temperature is the temperature above which a material is completely liquid. The Solidus temperature is the temperature which the alloy is 100% solid. The freezing range of the alloy is the temperature difference between the liquidus and solidus, where the two phases exist, for example the liquid and solid. So attached in the attached diagram, it is we can differentiate different types of a region. This is the liquid region, this is the liquidus line, and this is the solidus line, which separates solidus temperature at which the alloy is 100% solid. Solidus temperature is suppose this is the solidus temperature, this is the liquidus temperature, and over here for this alloy at this point the temperature is, we can within these two boundaries the mixture of liquidus and solidus crystal. The cooling curve for an isomorphous alloys during solidification is shown. The changes in slope of the cooling curve indicate the liquidus and solidus temperature. This is the cooling curve. This is one sample temperature, which is 1280 degrees centigrade, or solidus temperature at this point. When this is further cooled down at this time, and the temperature decreases to 1240 degrees centigrade. Over here we can get the solidus temperature at 40% weight of the nickel. So later on we will study in detail how to find the composition of two allying elements when they are added with each other at different temperature and pressure. Example of phases. We must differentiate between single phase and binary phase isomorphous system. The sugar water syrup solution is one phase and solid sugar is another phase. We must in phase diagram we must differentiate different phases. So sugar water syrup solution is the combination of liquidus and solidus solution. We will consider this in one phase region, while the other phase when they are separated from the mixture of liquid plus solid. Suppose if we get a pure solid sugar, then this will be considered as another phase. Each has different physical properties. One is the a liquid, the other is solid. Water is pure liquid, the sugar is pure solid. Furthermore, each has different chemical properties or chemical composition. One is virtually pure sugar, while the other is the solution of water and the chemical formula of the sugar. When water and ice are present in a container, two separate phases exist. They are physically dissimilar. One is the solid, the other is the liquid, but identical in chemical makeup. Also, when the substance can exist two or more polymorphic forms, for example, having both FCC and BCC structures, each of these structures is a separate phase because their respective physical characteristics differ. Sometimes a single phase system is termed. The phase center cube has a coordinate number of 12 and contains 4 atoms per unit cell. The body center cube has a coordinate number of 8 and contains 2 atoms per unit cell. The simple cubic has a coordination number of 6 and contains 1 atom per unit cell. So we over here in in the iron carbide phase diagram, we must know about we must differentiate between FCC and BCC. That's why solubility limit. What is solvent? Solvent is a host or major component in solution. What is solute? Solute is a minor component. What is the solubility limit? Solubility limit of a component in a phase is the maximum amount of the component that can be dissolved in it. For example, alcohol has unlimited solubility in water. Sugar has a limited solubility, while oil is insoluble in water. Why phase diagrams, or what is the importance of the phase diagram? A knowledge and understanding of phase diagrams is important to the engineer, which relates to the design and control of heat treating procedure for the different substances or different alloys. Some properties of materials are functions of their microstructures and consequently of their thermal histories. Even though most phases represent stable or equilibrium states and microstructure, they are nevertheless useful in understanding the development and preservation of non-equilibrium structures and their attendant properties. It is often the case that what is phase equilibrium? A system is at equilibrium if its free energy is at minimum under specified combination of temperature, pressure, and composition. In a macroscopic sense, this means that the characteristics of a system do not change with time but persist indefinitely. That is, the system is stable. A change in temperature, pressure, or composition for a system in equilibrium will result in an increase in the free energy and in a possible spontaneous change to another state whereby the free energy is lowered. Concept check. What is the difference between the states of phase equilibrium and metastability? We have studied phase equilibrium in this lecture, while metastability up to the students. So it's your assignment to differentiate between the phase equilibrium and metastability. However, you can find out the answer by going through this website. You can study you can differentiate between the states of phase equilibrium and metastability in detail. Microstructures. We must know about the microstructures because when we study phase diagrams, it is important to know the micro level properties of the substances. Microstructure is subject to direct microscopic observations using optical or electron microscopes. The physical properties and in particular the mechanical behavior of a material depend on the microstructure. The mechanical behavior and the physical properties both depends upon the material upon the microstructure of the material. In metal alloys, the microstructure is characterized by the number of phases present, their proportions, and the manner in which they are distributed or arranged. The microstructure of an alloy depends on such variables as the alloying elements present, their concentrations, and the heat treatment of the alloy. For example, the temperature, the heating time at the temperature, and the rate of the cooling to room temperature. For example, in iron carbide diagram, suppose if we add the composition of carbon at 0.8%, we can get different allying element. Or suppose if we increase the composition of carbon, if we change the composition of carbon at from 0.8 to 2%, we can get different allying element. Or if we increase the percentage or the composition of carbon from 2 to 4.3%, the property of the allying element of the iron in iron carbide diagram, we can get the cast iron rather than steel. Below composition of carbon below 2%, steel is formed, and beyond 2. After appropriate polishing and etching, the different phases may be distinguished by their appearance. For example, for a two-phase alloy, one phase may appear light and the other phase may appear dark. When only a single phase or solid solution is present, the texture will be uniform except for grain boundaries that may be revealed. The example This is one example from the research paper published in 2018, in which the study for the influence of ultra fine grained and coarse grained microstructure of titanium alloy Ti6Al4V on the strength of the diffusion bonded joint. So this was studied using the Liberty DB fixture and a new shear test rig. The DB process was carried out at 725 degrees C and 825 degrees C during 2 and 4 hours in a vacuum furnace. So different experimental procedures are published in this paper. So for the 2 hour and 4 hour vacuum furnace results are also published. In the preceding slide we will present some titanium alloy microstructures of titanium alloy. This is one example of the microscopic observations. Two figures are attached. In figure A, we can see two phase boundaries, the the light region and the dark region. Similarly, in B, 30 micrometer resolution, three types of phase boundaries can be observed over here. The other is dark region, white region, and some gray sparks can be seen in this figure. This is one example of titanium alloy when cooled at different cool down at different temperatures. The titanium alloy is studied. This figure is being taken from that published paper. What is one component or unary phase diagrams? There are three externally controllable parameters that will affect phase structure. The temperature, pressure, and composition. Phase diagrams are constructed when various compositions of these parameters are plotted against one another. For one component system in which composition is held constant, the one example is phase diagram for pure substance. This means that the pressure and temperature are the variables. This one component phase diagram or unary phase diagram, sometimes also called pressure temperature diagram, is represented as a two-dimensional plot of pressure, ordinate or vertical axis versus temperature, abscissa or horizontal axis. Most often the pressure axis is scaled logarithmically. This is one example taken from the book of engineering material written by Celester in chapter 9. One example of unary phase diagrams in which three types of phases of water are shown. One is solid, the other is liquid phase, the third phase is vapor. Are separated by a triple point at position O. One horizontal line is drawn at an atmospheric pressure, 1 atmospheric pressure. If we go horizontally from left hand side to right hand side at a temperature of 0 degree centigrade, about 0 degree centigrade, the from minus 20 or minus 25 degree centigrade to 0 degree centigrade, the water is solid ice. Similarly, at constant pressure, 1 atmospheric pressure, when we give heat to the water, when we add heat to the water, when that region is crossed, the solid boundary is crossed, the water is converted from solid to liquid. From at point 2, similarly at point 3, we can touch the boundary which separates the liquid from vapor. At point 3 and at a temperature about 98 degrees centigrade, the liquid state of water is converted into vapor state. This is a pressure temperature phase diagram of water. The intersection of the dashed horizontal line at 1 atmospheric pressure with solid liquid phase boundary. So different phases. This is one example of the unary phase diagram. Here is another example for the two types of variable, temperature versus heat. For the water, the flat lines on the graph show that even though substances is continuing to be heated, there is no change in temperature of the substance. This one is one flat line, the other flat. The temperature, the heat is continuously added from this point to this point, but no change. The water, the condition is still ice plus water. There is no change in temperature. Similarly, for this one, the heat is continuously added at a condition of water plus vapor, but there is no change in this phase within this region. During this stage, the energy is going to weaken the bonds. Here we can see the solid region. This is the generalized, it is not to the scale. This plot is not to the scale. Solid ice, given when heat is added until this region, we can get the solid ice. And similarly, at this heat, the liquid, the phase is liquid, and at last, at this range, when heat is added in calories or in another unit, the water plus vapor region is converted into gaseous state. This flat line in water plus vapor, the bonds are breaking when heat is added, or when heat is taken out, the bonds are reforming from vapor to water plus vapor. This is the boiling point or condensation point. This is called the boiling point or condensation point. When the water is converted from liquid state to vapor state, we can get the boiling point, or if water is cooled down from gaseous state to liquid state, we can get the condensation point. This is the bonds are weakening or strengthening when in ice plus water phase region. When ice is converted to water, we can get the melting point, or when heat is taken out from concept check. Why is the flat line from solid to gas or gas to liquid is so much longer than the flat line from solid to liquid or liquid to solid line in the temperature versus heat diagram of the water in the previous slide? It takes a lot more energy to break or reforms the bond than it does to weaken or strengthen them. Identifying substances. Let's say you come across an unknown solid substance. How will you identify the substance? One way is to apply heat and graph its phase diagram. We will be able to identify the substance. Binary phase diagrams. Binary phase diagrams in which temperature and compositions or variable parameters and pressure is held constant, normally at 1 atmospheric pressure. We have already explained one example of binary phase diagrams. The other example, binary alloys, those that contain two components. Binary phase diagrams are maps that represent the relationship between the temperature and the compositions and quantities of phase at equilibrium, which influence the microstructure of an alloy. Many microstructures develop from phase transformations, the changes that occur when the temperature is altered. Ordinarily, Upon cooling, this may involve the transition from one phase to another or appearance or disappearance of a phase. Binary isomorphous system. We can explain the binary isomorphous system with respect to the attached in the upcoming slide, the attached figure in the upcoming slide in figure 9.3a. Temperature is plotted along the ordinate and abscissa. The abscissa represents the composition of villi, or the horizontal axis represents the composition of villi. Two types of two allying elements. One is the copper, the other is nickel. They are represented, the copper and nickel are represented in weight percent bottom and atom percent on the top of the nickel. The composition ranges from the 0% by weight nickel or 100% by weight copper on the left. Horizontally, extreme and similarly 100% by weight of nickel or 0% by weight of copper on the right hand side. First, for metallic alloys, solid solutions are commonly designated as lowercase Greek letters. So we must know about the representation of the solid solutions for different allying elements or different substances. The solid solutions are represented by alpha, beta, or this is the phase diagram, binary phase diagram for the copper nickel phase diagram. A portion of the copper nickel phase diagram for which composition and phase amounts are determined at point B. If we look at the phase diagram over here, it's 0%. From the left hand side, it's 0 point. Copper composition is 100%, while nickel composition is 0%. And at right side, the nickel composition over here is 100%, while copper composition is 0%. The vertical axis is the temperature when heat is added to the substances. When heat is added to the substances, at the extreme left, when copper is heated, first the melting point of the copper is reached at 1085 degrees centigrade. The solid alpha copper is changed to the mixture of solid plus liquid solution, because there are two solutions. One is the copper, the other is nickel. When the melting point of any of the substance is reached, that substance changes from the solid to liquid, while the melting point for nickel is greater as compared to the copper. That's why nickel is still solid solution at this region at 1085 degrees centigrade. Similarly, after crossing the temperature, the melting point of the copper is crossed 1085 degrees centigrade, and when the composition is added, some small percentage of nickel is added to the copper solution, and then when it is heated, suppose it's 60% by weight of copper and 40% by weight of nickel. If we heat that substance, we can get over here both the substances are in solid solution. When the boundary line, the Solidus line, is crossed at a temperature of about 1300 degrees centigrade, we can get the solid alpha plus liquid region, and similarly when the Liquidus line is reached, we can get a completely liquid solution of both the substances. But how to find the composition of the both substances when there are two substances given at a particular point? We will study, we will calculate we will find out the composition at any point in a phase diagram with the help of tie line or lever rule. But in this general phase diagram, in any type of phase diagram, we must know about the types of phases. Like in this given phase diagram of copper nickel, we can see three types of phases: the liquid phase, and a mixture of liquid and solid solution phase, a pure solid solution. And similarly, we must differentiate between the boundary lines. The Liquidus line is the line which separates the liquid solution from the mixture of liquid plus solid. Similarly, the Solidus line is the line which separates, is a boundary which separates the Solidus solution from the Liquidus line. Here it's a bit more explained. Three different phase regions or fields appear on the diagram: alpha field, liquid field, a two-phase alpha plus liquid field. Each region is defined by the phase or phases that exist over the range of the temperature and compositions. The liquid L is a homogeneous liquid solution composed of both copper and nickel. The phase is substitutional solid solution consisting both copper and nickel atoms and having an FCC crystal structure at temperature below 108 degrees centigrade. Copper and nickel are mutually soluble in each other in the solid state for all composition. This complete solubility is explained by the fact that both copper and nickel have the same crystal structure FCC. When two substances having the same crystal structure FCC or BCC, they are both soluble in solid state as well. Or if they have nearly identical atomic radii and same electronegativities or and similar valences, they are soluble with each other. The copper nickel system is termed as isomorphous because of this complete liquid and solid solubility of two components. What is termed isomorphous? Isomorphous. The copper nickel system is termed isomorphous because of this complete liquid and solid solubility of two components. Why they are solid, completely liquid, soluble, liquids, and they are soluble in liquid state as well as in solid state, because of the same valence shells, because electrons, because of the same electronegativities, and because of the identical atomic radii and same crystalline structure. Eutectic phase diagrams. What is eutectic? Show on a solid liquid phase diagram where is eutectic located. Many alloys are based on only two elements. A good example is lead tin system, which is used for soldering, but because of the toxicity of lead, it is now being replaced with another 10 alloys. The solid solution alloys, a single phase solid solution forms during solidification. The example is 10 2% by weight with 10. Lead 2% by weight with 10. These alloys strengthened by solid solution strengthening, by strain hardening, and by controlling solidification process to refine the grain structure. A eutectic system has two components and they have limited solubility. Upon cooling, the liquid will transform into mixed solid phase. We will use the lead tin phase diagrams as an example. Phase is a solid solution of tin with lead is a solute. This is the phase diagram for lead tin system in which different regions are explained with respect to the temperature and composition, and pressure is held constant, which is 1 atmospheric pressure. This red line is a Solidus line which separates the solid solution from the mixture of liquid plus alpha region. The Solidus solution of lead is purely represented by alpha. It is a pure Solidus crystalline solution of the lead. The beta is the pure solid solution of tin. This region is mentioned on the right hand side. On the left hand side, in horizontal axis, the lead composition is 100%, which is varied, which is reduced as we go to the right hand side. On the right hand side, on the horizontal axis, the tin solution is represented as 100% composition by weight. When we go from right hand side to the left hand side, the composition is decreased by 90, 80, 70, and similarly to 0% by weight on the extreme left side. The 0% by weight is a tin solution. We can explain this in other words that lead is 100% by weight and tin is 0% by weight on the left hand side axis. The Liquidus line, this is the Liquidus line represented by L, and this separates the pure liquid solution, homogeneous liquid solution, from the liquid plus Solidus solution of the lead. The horizontal line is called Eutectic line, which is plotted from 19 to 97.5. This is called the Eutectic line. The solvents line starts from the origin to the 19, the solvents line. From the last slide, what is the eutectic point and what is the eutectic temperature? The point E, if we look at point E, the point E is called the eutectic point. Why we call it eutectic point? Because it's a Greek word which is defined for the homogeneous mixture of substances that melts or solidifies at a single temperature that is lower than the melting point of any constituents. If we look at this diagram, the eutectic phase diagram, this is the lowest point of the lowest melting point of the two solid solution, the mixture of the two solid solutions, in which we can easily solidify or we can easily melt the substances when they are mixed together. So if we cool down after melting, if we cool down both the substances, a point is reached or a temperature is reached where after increasing or decreasing that temperature, the substances are either solidifies or converted to melting phase. So that's why the temperature at which the eutectic point is called a eutectic temperature. The eutectic point is the lowest point, the temperature at which the particular eutectic mixture freezes or melts.